right, so if we flip 3 coins, how many possible outcomes could we get? What you got, Zach?
4.
4 outcomes? What do you think?
8.
8? 8? All right, so what are they?
3 heads, 2 heads and a tails, a head, a tail, and a head, tail and 2 heads, a head and 2 tails, tails, head, tails, 2 tails and a head, and 3 tails.
Absolutely, yes. So there's 8 different possible ways for us to get them. Well, yes, order matters. Yeah. Yeah, what is the first coin? What is the second coin? What is the third coin? Yeah. Yep. Okay. How else could you have gotten 8, by the way? Did anybody use like math, maybe? What did you do?
You just multiply, like, if there's like 2 outcomes for each one, you can just multiply 2.
So 2 times 2 times 2
Yeah.
also gives us 8. That will come back later. Yes. But today we're doing mostly let's write them out. What is our sample space? What could actually happen? Okay? So if we have 8 possible outcomes, what's the probability of getting all 3 tails? 1 out of the 8. Good. So flip them 3 tails, 1 out of the 8. Okay? How about rolling a 6-sided die? How many outcomes are there? 6, right? There's 6 sides, so 6 possible ways. So what's the likelihood of rolling an odd number? 50%? 1, 3, or 5, right? That's 3 out of the 6, which is 1/2 or 50%. Good. What about rolling 2 6-sided die? 36 this time. Okay? Yeah, so if you can roll a 1, and then you could roll 1 through 6. You could roll a 2, and then 1 through 6 again, right? So using that math kind of from before, if you did 6 times 6, that also gives you the 36 possible outcomes. I have them all listed for you out there. What's the possibility that you roll a sum greater than 3? Yeah, there's a couple ways to go about it. Okay? If you look up there, what's in red are all the possible ways to be greater than 3. Okay? So 33 out of those 36 possible outcomes, when you add those numbers together, it's bigger than 3. Okay? You could also go the opposite route. See how I circled 3 of them? The combination of 1, 1, 1, 2, and 2, 1 are the only ways to get a sum of less than 3 or less, right? So out of 36, 3 of them don't do it. So I can take 3 out of 36 to get 33. Okay? So a couple ways to go about it. We are going to come back to that. That is a strategy that we're going to use later. To kind of go like, it's almost like a shortcut. Like, oh, well, I can see what's not happening there. Take that away. Okay, so about 91.7%. Questions about any of your warm-ups? Are we in the probability mindset?
Yeah.
Awesome. All right, so let's talk about some probability. A big thing we're going to talk about is sample space. Okay? A probability experiment is an action or a trial that has varying results. The possible results of a probability experiment are the outcomes. And a collection of one or more outcomes is called an event. The set of all possible outcomes are called a sample space. Okay, so that's everything in words. Let's look at an actual example of a probability experiment. Okay, so the experiment is the action: rolling a dice, flipping a coin, picking a card, spinning a spinner. Okay, that's the experiment. Okay, so my example for this one will be rolling a 6-sided die. That's the experiment. Okay, what is the sample space when you roll a 6-sided die?
What?
What's the sample space when we roll a 6-sided die? So what's the possible outcomes? 1, 2, 3, 4, 5, or 6. Right? That's my sample space. what's an event? So an event is like, what's the chances that I get blank? So let's say rolling an even. Okay, what's the that's the event. Rolling. Bless you.
Bless you.
Bless you.
Bless you.
Rolling an even. Rolling a number bigger than 4. Rolling the number 1. Right? So it's like, hey, what are the chances that this happens? That's the event. Okay? And then the outcome is what actually happens. So if I roll a die and I roll, let's see, rolling, I don't know, a 3. That's the outcome. Okay? So the experiment is tossing it. Sample space, what could happen? Event, what am I trying to see could happen? Outcome, what actually showed up. Okay. So let's look at a couple of finding sample spaces, because sample spaces are a big deal. I have to know the probability of something comes out of the possibility of what could happen out of everything, which is our sample space. Okay. So what if we flip a coin and we roll a 6-sided die? How many possible outcomes are there in the sample space? So using the math way, there's 2 sides to a dice, right? There's 2 sides to a coin, 6 sides to my dice, 2 times 6, there's my 12, okay? But list the possible outcomes. So we know it's 12, but what are they? Okay? If I flip my coin, what are the possible outcomes? If I flip a coin, what are my outcomes? I can get a heads or I can get a tails, correct? And then after that, when I roll my die, I can get a 1, 2, 3, 4, 5, or 6. 1, 2, 3, 4, 5, or 6. So does that prove 12 possible outcomes?
Yes.
Yes. Because we had heads 1. We can get a heads and a 2. Heads and a 3. Heads and a 4. Heads and a 5, heads and a 6. And then vice versa. We could have gotten a tails and then rolled a 1. Tails rolled a 2, tails 3, tails 4, tails 5, and then tails 6. So 12 possible outcomes. So that is the sample space. Okay, so what if I up it to 2 coins in a die? What do you think then? You think it's going to be 24 now? Yeah? So let's see if our theory is correct. Oh, we're going to. You ready? So if I do 2 coins, the first coin, we know, can be heads or tails. And then if I flip another coin, that could also be a heads or a tails, right? And then off of each one of those, we have our 6 options, correct? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So how many outcomes is that? 24.
You should also made it in random order. That was a lot more.
But this is what could happen. Okay? If it tells you to list the possible outcomes, that's what it wants to see. Am I going to make you do that every time? No. Today's an introduction day, so we need to understand exactly what is that sample space. Okay? 2 heads with 1, 2 heads with 2, 2 heads with 3, 2 heads with 4, 2 heads with 5, 2 heads and 6. And that just repeats. Okay. Now we're going to get into different kinds of probability. Okay. The first type of probability we're going to look at today is called theoretical probability. Okay. The probability of an event is a measure of the likelihood or chance that the event will occur. Probability is a number from 0 to 1, which includes the 0 and the 1. So 0 shows impossible or 0%. 1 means certain or 100%. Okay? And can be expressed by a decimal, a fraction, or a percent. So we usually set it up with the fraction and then convert that fraction into a decimal or a percent afterwards. Okay? The outcomes for a specified event are called favorable outcomes. When all outcomes are equally likely, the theoretical probability of the event can be found using the following: number of favorable outcomes divided by the number of total outcomes. Okay? The probability of event A is written as P of A, like that. We're going to use lots of like A's and B's or something like that.
Been used for correlation as well.
Kind of, yes.
It's not.
Oh, yeah. Except we don't go negative.
Yeah.
Yeah. Yep. Okay, so theoretical is theoretically this should happen. Okay, this is how our brain works. If I say, hey, what's the probability of flipping a coin and getting heads?
50.
Your first thing is 50-50, right? Is that what's actually going to happen if you flip the coin? If you flip it 10 times, are you guaranteed 5 heads, 5 tails? No. But theoretically, that is what should happen because they're equally likely to occur. All right? That's the first kind of probability we're going to look at. First one is we have a student, maybe some of you in here, that would just, I don't know, randomly guess at 4 true-false questions. Okay, all right. What is the probability that if you did that you would get 2 of them right? Okay, out of the 4. So we have to list the number of outcomes first to get our sample space, then see the probability of getting exactly 2 correct. Okay, so number correct, we could get none correct, right? We could get 1, we could get 2 correct, we could get 3 correct, or 4 correct. Okay? I'm going to use I's for incorrect and C for correct to show what could happen. So they could all be wrong, right? Wrong, 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 wrong. That's all incorrect. Or I could be very lucky and get them all right. Correct, 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 correct. I could get just one of them right. So the first one could be right and the rest are wrong. Or it's the second one that's correct. Might be just the third one. Or it might be the last one. It's mirror image for getting 3 correct. You can get the first 3 right. First 2, then the last one. Those are all the ways to get 3 of them correct, meaning you only miss 1. And then there's getting 2 of them correct. There's a couple of different ways this could happen. Okay. I could miss the first 2, get the last 2. Or I could get the first 2, miss the last. Get the first and the last. Miss the first and the last. Or we could flip-flop. Right, wrong, or vice versa. Wrong, right, right. So using all of our possible outcomes, what is our sample space? In total, how many outcomes could possibly happen? 16. There's 16 possible ways I could randomly guess true, false questions and what I could get right and wrong. So how many of those 16 were getting exactly 2 of them right? The 6. So the probability of event A is going to be 6 out of the 16, which does simplify to 3 over 8. As a probability, though, we typically write it in decimal or percent form. So we're going to say 0.375 or 37.5%. So what would your chances be getting all of them right?
1 over 16.
Which is what?
16.
It's about 6%. Yes. Yeah. It's about 6% chance, which is the same as if you got them all wrong. Okay. So you're most likely getting at least 2 of them right if you look at our outcomes there. Those are your best chances. What's up?
Do you know the thing where it's like there's 3 doors and one of them has a goat and one of them has nothing?
Another kind of probability you've already done, you just didn't know the name of it. Remember in our warm-up, the third one, where it was like the sum of 3? And we're like, oh, well, instead of counting all 33 ways, I can see that 3 of them, right, were less than 3. That's called a complement, okay? So what's not going to happen. The sum of probabilities of all outcomes in a sample space is 1. So when you know the probability of event A, you can find the probability of the complement, is what it's called. Of event A. The complement of event A consists of all outcomes that are not in A. So technically that's what we did in our third warm-up problem. It's denoted by a bar. So this book uses an A with a bar on top. Other notations you might see is called a tilde, like a little squiggle in front of an A. That also means not A. This book sticks with the A bar though, so that's what we're going to stick with. I wanted you to see both ways. Okay. So the probability of the complement of event A is probability of A bar equals 1 minus the probability of A. Okay. So let's use the complement to find a couple of probabilities. So here I've shown you all the results of rolling 2 6-sided die. What is the probability that the sum is not 6? Okay, you think? How'd you get that? Okay. So 1 minus the probability of a sum of 6, right? 1 minus, so how many, so he took out the ones that were a sum of 6, right? So 5 and 1, 4 and 2, 3 and 3, 2 and 4, 1 and 5. So 5 of them are a sum of 6. So if we take those out, that's 31 over 6, which is about 0.861.
Could you explain again what the A bar is?
Complement. It's not A. The sum is not 6.
What isn't A? Like,
A is the event. So in this case, the A is a sum of 6. So
Okay.
A bar is not a sum of 6.
Okay, that makes sense.
Mm-hmm.
That makes sense. And that's called the complement of
The not, yes.
Okay.
Not something is the complement of something. Yep. So the sum is less than or equal to 9. So what would the complement of that be?
What is not? What's greater than?
1 minus the probability of a sum greater than 9. So we're looking for sums of what? 10, 11, or 12. So this is nice when there's fewer of those. So 10, 11, or 12, where's that at here? 10, here's my 10s, 11, and 12. So there are 6 of them. So 1 minus 6 over 36 will give me about 0.833. What's that? Correct. So the opposite would just be greater than. I can't be equal to it. Yeah, the opposite is not less than. It's okay. No, someone asked me that every class so far. So the complement is not less than and not equal to. Does that make sense? Which leaves me with just greater than.
Oh yeah.
Mm-hmm. No, that's good. I'm glad you asked that. Okay. Okay, so we have done theoretical. We've talked about complements. Now we're going to do a little throwback Monday action. Okay. Some probabilities are found by calculating a ratio of 2 lengths areas or volumes. Such probabilities are called, what do you think? Geometric.
Oh yeah.
Oh, yeah. Geometric probabilities. Okay. These are usually like when you're looking at games and points and what are the chances that I can do this. It's all based off of shapes and areas on a board. Those are all geometric probabilities. Okay. So our first one is throwing a dart at a board, which is shown. Your dart is equally likely to hit any point inside of the square board. Are you more likely to get 10 points or 0 points? So let's talk about this expression right here. Equally likely to hit any part. That means it's a fair board, okay? There are such things as not fair, like not fair dice or weighted dice. People use them to cheat, right? So your outcomes are not 1 out of 6 because they got little weights in there. They're going to make sure they roll a certain thing, right? So to say it's equally likely to hit any part of the board is saying that it's a fair board, okay? Nothing is leading the darts into a certain area. It's all the same material. No secret magnets. Nope. Okay. So that's what that means. Okay. Obviously, the different areas of the points changes your likelihood of how many points you can get. Does that make sense? So what area of this board is just 10 points? What area of this board is 0 points? Is what this is asking me. Okay. And then which one is more likely for us to hit? Because there's more space for our dart to land. Okay. So let's do the 10 points first. Let's just do the little circle on the inside. So what's the area of the little circle versus the area of the entire board? Okay. So yeah, for circles, we got to do pi r squared. So the probability of getting 10 points. What's the area of this little guy right here?
1.
No.
1 times 5.
No.
What?
Look, 3 inches. 3 inches,
Oh, each of
3
those
inches, 3 inches. Yeah. So this is 3, right? So the probability of the circle, or the area of the circle, excuse me, is going to be pi r squared, so 9 pi. Out of the area of the entire board. Well, it told me it was a square board, right? That was nice. But I need to know one of the sides. So what is a side of the square?
3 inches.
Nope. 18. Where did 18 come from?
There's 3, 6, 9.
Yes, good. 3, 6, 9, right? I'm not going to sing the song. 12, 15, 18. So it's 18 inches across the board. So, and for a square, we're going to do 18 squared, which is 324. So 9 pi over 324 is about 0.087.
Could you
Okay?
explain to me why we're doing over 18 squared?
Because it's out of the entire board.
Area.
Mm-hmm. Yep. So about 8.7% of the board is worth 10 points. Okay? So now let's find 0 points. Okay? So that's everything outside of my circle, right? So my whole board, which we already know is 18 squared, my whole board minus what's the entire circle? That's going to be pi 9 squared. So 324 minus 81 pi. Divided by the entire board, which we know is 18 squared. Which is 324. So figure that out while I get my plug. What is the area, or what percent of my board is worth 0 points? What'd you get?
21%.
About 21%? Yeah? So it was about 0.215. So about 21.5%. So are you more likely to hit 0 points or 10 points?
0.
More likely to get 0 points. Does that make sense? Does our math make sense? Yes. Usually the more points it's worth, the smaller the area is. Remember when we did sticky ball? Did I make the big circles worth less and the smaller circles worth more? Yes. So it is more likely. Where's my words? Here we go. It is more likely to get 0 points.
Is A or 1?
Yes.
Okay.
Yep. All right. Last kind of probability today is called experimental probability. That's the last kind we're going to look at. So we've done theoretical, we've done complements, we've done geometric. The last one today is experimental. Okay. So, an experimental probability is based on repeated trials of a probability experiment. The number of trials is the number of times the probability experiment is performed. Each trial in which a favorable outcome occurs is called a success. The experimental probability can be found using the following: number of successes over the number of trials. So experimental probability is what actually happens. So theoretically, heads or tails 50-50. But my experiment, if I flip the coin 10 times, what did I actually get? That's the experimental probability. Okay? So theoretical is what should happen. Experimental is what actually happens. Okay? You're conducting an experiment. That's the action. What did you actually get? So we got 2 examples of this one. Our first one, we have a spinner. Okay? Each section of the spinner shown has the same area. The spinner was spun 20 times. The table shows the results for which color. The table shows the results, period. For which color is the experimental probability of stopping on the color is the same as the theoretical probability. Okay? Well, what is the theoretical probability of landing on a color? 1 out of 4. Good. So theoretically, theoretical probability is 1 out of 4 or 0.25. Okay. They spun it 20 times. And this table shows me the result. So red got 5, green got 9, blue got 3, yellow got 3. Which one of those is the same as the theoretical probability? They're red. Good, because that's 5 out of 20, right? 9 out of 20. 3 out of 20. 3 out of 20. 5 out of 20 simplifies to 1 over 4 or 0.25. Okay. So red experimental probability is the same as the theoretical probability, because 5 over 20 equals 1 over 4. So they are the same. How about you try the last one with my shells? I will read it out loud, and then you're going to do it. Here we go. Example 6. You randomly select a seashell from a collection and record the type of shell. The types of the first 90 shells you select are shown. What is the experimental probability that you select a Florida cone? Okay, so there's my results. You do this one. What is the experimental probability of selecting a Florida cone? All right, what do we get? 33 out of 90, which is what probability? Yeah, so what would that be? That's okay, that's correct. What would that also be as a decimal or percent?
1/3 times 33.
So probability of the Florida cone. So yes, the setup is there were 33 out of the 90, right? 33 out of 90. They told me 90 right here. Also, 33 plus 14 plus 8 plus 15 plus 20, 90. Okay? So that is how we set it up. That equals about 0.367. So the experimental probability of selecting a Florida cone is about 36. That's ugly. 36.7%. Bonus question: what was the theoretical probability of picking the Florida cone?
Really don't know.
Well, based off of the kinds that were picked. 1/5, right? There were 5 types. So theoretically, only 5 types were picked. Theoretically, 1 out of 5. But what actually happened was out of the 90 actual picks, 33 of them were the Florida cones. Okay? Good.